Hello viewers, in this video I'm going to be showing you how to prove this relationship. And so we know that our operator, this is equal to partial derivative with respect to partial derivative of x plus that of y plus that of z. And we also know that our gradient operator is given by this all over z. And so because the first operator without phi is expressed this way, and then when phi is added, this is gradient operator, we have that the phi partial derivative of phi with respect to x, partial derivative of phi with respect to y, and partial derivative of phi with respect to z. So we can call this equation 1, and then we call this equation 2. And so if we have to bring this and this together, we are going to have this dot this means divergence. So this is equal to this, and so this dot is a dot product multiplication. So we are going to have, taking this first, plus all over this plus. So we are done with this. So we now consider this is a dot product multiplication, which is the all of this now. So we take it partial derivative of phi with respect to x plus partial derivative of phi with respect to y plus partial derivative of phi with respect to z. Okay, so since we are done with that, we can, since it is dot product multiplication, from here we can now multiply them. So when we say this multiplying this is going to give us partial derivative square phi over partial derivative x square plus this multiplying this give us this, and this multiplying this will give us this z square. And so we have that this into is equal to this. But haven't done this, we can call this is equation 3, and let's call this equation 4. Let's call that equation 4. Okay, so remember we are asked to prove that this is equal to this. So that's what we're asked to prove. So we are still in the process of achieving that. So let's say factorize the right hand side of this equation. So this is the left hand side of the equation, this is the right hand side. So I said factorize the right hand side of equation 4. Yeah, this is equation 4. So let's write the left hand side first. So if we are to factorize this, it means we have to bring out the value of phi, because phi is common here, phi is common here, phi is common here. So if we bring out phi, we are going to have partial derivative square all over change partial derivative x square plus here we are going to have this, and here we are going to have this. And so since phi is common, so because if we now say phi times this, we are going to have this. Phi times this, we are going to have the all of this, and phi times this, we are going to have the all of this. Okay, so having achieved that, we continue. But we have to know that, recall that this square is equal to so we can call this equation 5 and we call this equation 6. So if we now say that, a Laplacian operator, this one is Laplacian operator, this is called Laplacian operator. So if we say that a Laplacian operator is equal to the all of this, so we are now saying that this Laplacian operator is equal to this. So if we now replace this value in equation 6, in equation 5 rather, we now replace this value because we have established that the all of this is equal to this Laplacian operator, as the all of this value is equal to this Laplacian operator. So let's replace it in equation 5 so that we have a new equation to be this, to be equal to the all of this is replaced with a Laplacian operator, and then we still have phi multiplying it. So this is equation 7. So if you look carefully at equation 7, you understand the fact that it is the same thing as what we were asked to prove. It is the same thing as what we were asked to prove. So we've been able to show that this is equal to this. Thank you.